Welcome to another episode of Unlearning Unlicensed. In this video series, I am going through RF Elements educational content, and I am correcting the myths, misconceptions, and misunderstandings that RF Elements created so that they could sell more of their antennas. In this video, I'm talking about beam efficiency, which RF Elements describes as the most important antenna parameter. As far as I know, RF Elements is the only antenna vendor that uses beam efficiency as an antenna parameter. That doesn't make it very useful as an antenna parameter because most WISPs use antenna parameters as a way of doing product comparison, as a way of comparing this antenna versus that antenna. And if only one vendor is using an antenna parameter, that doesn't make it very useful. But you don't need to take my word for it. We can just hop right in. Here we go.
I'm Tomar Zolensky, and I'm a product manager at RF Elements and marketing manager at the same time.
So he says he's the product manager and he's the marketing manager at the same time. And I think the problem here is that he's leaning into his role as the marketing manager a little too much and his role as the product manager not enough. So the role of the product manager is to develop the products to meet the needs of the customers, whereas the role of the marketing manager is to convince the customers that these products meet their needs. And I think that you'll see with beam efficiency, it's much more marketing and much less product.
And my promise for today to you is that you will learn what beam efficiency is. Why do we actually think it's the most important antenna parameter in WISP networks? As well as you will also learn about the other antenna parameters that are usually thought or known for showing the ability of an antenna to deal with noise. So let's start. So the parameters that are usually considered relevant when speaking of the ability of an antenna to mitigate interference are front to back ratio, side lobe levels, or ETSI masks. These you most likely know or at least heard about. The one that RF Elements believe is the most important one in terms of noise suppression is beam efficiency.
So this is interesting. It says these are the noise rejection related antenna parameters. And he lists out front to back ratio, yes. Side lobe level, yes. ETSI mask, yes. Beam efficiency, sure. But he ignores beam width, especially in a point to multi-point sector antenna. Beam width is one of the main parameters that you would look at when dealing with noise. So the difference between a horn antenna and a sector panel antenna is mostly beam width. Sector panel antennas usually tend to have wide beam widths, 120 degrees or 90 degrees, maybe 60 degrees. But with those wider beam widths, you're picking up noise from the entire sector. If you have a 120 degree beam width, then you're picking up noise from that entire 120 degree sector. Now, if you have a 30 degree beam width, you're picking up a lot less noise and interference from that main lobe. So the beam width is one of the key antenna parameters that you should be looking at when thinking about noise rejection. And RF Elements totally misses that.
Beam efficiency is the ratio of the main lobe energy to the total energy an antenna radiates.
Keyword there is radiates. So he says beam efficiency is the ratio between the energy in the main lobe, the total energy an antenna radiates. There's a lot of energy that is lost before the energy radiates. There's VSWR, or return loss, which is the amount of signal that an antenna reflects back at the radio. And that is lost energy, but not accounted for with beam efficiency. There's cable loss or conduction loss, where the electrical energy is lost before it is converted to radio waves. And then there's loss within the antenna too, due to things like the radome, where the energy is absorbed by the antenna. And again, it's not radiated. So beam efficiency doesn't account for any of those losses. And what's interesting is that while focusing on beam efficiency, they dismiss other antenna parameters such as gain, which actually do account for all of those losses, because gain is the measurement of the antenna's ability to efficiently focus energy in a specific direction. It is measured relative to a perfect isotropic radiator. In other words, an antenna that is radiating perfectly in every direction. So gain will account for VSWR. It will account for cable loss. It will account for the loss of energy by the radome. Beam efficiency, although it's called efficiency, it's not measuring antenna efficiency. It's only measuring the energy that essentially leaves the antenna. It's not talking about any of the efficiency of energy before the signal leaves the antenna. And that's one reason why beam efficiency is really an incomplete antenna parameter. Certainly not the most important antenna parameter, because it doesn't account for antenna efficiency, despite the name. The other thing that's important to notice is that they're defining it as the energy in the main lobe relative to all the rest of the energy that the antenna radiates. They're defining the main lobe, the main beam, up to the first null, but they don't define the first null. So when you look at antenna patterns, especially across a frequency range, you'll notice that a lot of times the side lobes, the largest side lobes, emerge from the main lobe. At what point does the main lobe end and the side lobe begin? If you don't clearly define that, which they haven't defined that, then that's a subjective measurement. You say, well, to me it looks like this is the main lobe and that's the side lobe, but who's to say? You need to clearly define what is the first null. Without clearly defining that, then beam efficiency just becomes subjective. Who's to define the main lobe? Elements? I don't think so.
Now it says how much of the total signal energy is contained in the main lobe. As simple as that. So the maximum beam efficiency value is 100%, which is an ideal situation. That's really the ideal goal we desire.
The ideal goal we desire is not 100% beam efficiency. The ideal goal that we desire is that 100% of the radiated power is sent towards the receiving antennas. In the case of a point-to-multipoint network, sent to the stations within the sector. And in the case of a point-to-point application, you want to send that to a single point. It's not that you have it all within the main lobe. The main lobe can still be sending signal in unintended directions, particularly in point-to-point. That's most obvious in point-to-point. So in a point-to-point application, it doesn't matter if all of the signal is contained within the main lobe, if the main lobe is still sending the signal in undesired directions. And similarly, the same can be true for point-to-multipoint with a sector. So you could have a 60-degree sector, and you could have all of your stations within that 60-degree sector. But 60-degree sectors are often defined as half power beam width being 60 degrees. So there's still a lot of power within that main lobe, within that main beam, outside the 60-degree sector that is wasted power, and you're picking up extra noise from the main lobe. So beam efficiency doesn't account for wasted energy if that energy is within the main lobe. So you really have to think about the shape of the beam, not just essentially the antenna pattern, not just whether it's in the main lobe or not within the main lobe.
And the smaller the beam efficiency is, the more side lobes an antenna has. Since antenna side lobes are the direct cause of problems in WISP networks, antennas with a lot of side lobes should be avoided at all costs.
So he says antenna side lobes are the direct cause of noise in WISP networks. They're not the only cause of noise within WISP networks. Again, a lot of the noise in WISP networks is picked up within that main beam, particularly with point to multi-point sector application. You're going to be picking up noise from the entire sector. And you could be picking up noise from the side lobes, but the side lobes are not the only cause of noise problems on WISP networks.
The higher the beam efficiency of the antenna you use is, the better for your network and the end users of your services in the end. Beam efficiency is an antenna parameter not only to know about, but actually also factor it in when you're deciding on how to deal with the interference issues you may have in your unlicensed networks. Now here is a practical example. So this is the radiation pattern of a generic parabolic dish. And if its beam efficiency is 40%, the remaining 60% of the energy goes everywhere else. In other words, side lobes. Because any radiation outside the main lobe is a side lobe, well, obviously it must go in the side lobes. Note that all the side lobes are highlighted here, so beam efficiency includes all the side lobes an antenna has. If you want to compare two antennas in terms of side lobe performance, beam efficiency makes it extremely simple. The higher number wins. In this example, the ultrahorn on the left has beam efficiency 99%, so only 1% short of perfection. A generic dish antenna, on the other hand, has beam efficiency 40%, so the remaining 60% of the energy it radiates is in the side lobes. 99% is clearly more than 40%, and that's why ultrahorn is way better antenna in terms of noise suppression. In our opinion, the best on the market, to be honest.
So that depends again on whether the source of the noise is coming from the side lobes or if the source of the noise is coming from the main lobe. If the source of the noise is coming from the main lobe, then having high beam efficiency isn't going to help with noise. If the source of the noise is coming from the side lobes, then having high beam efficiency will help you reduce the noise. It just depends on where the noise is coming from. It depends on the shape of the beam. So it's also worth noticing that you could have much more focus on the main lobe, and you could have much higher gain on the main lobe, and then you have side lobes. Even in a noisy environment, it's quite possible that having the increased gain is going to be more helpful than reduced side lobes. So beam efficiency, although RF Elements likes to believe that beam efficiency is the number one parameter to care about with WISP application, no, you have to factor everything in. And the increased beam efficiency of the ultrahorn may or may not help with noise. It just depends on really where the noise is coming from.
But to be fair, let's also have a look at the parameters you may already know. Front-to-back ratio is one of them, and many manufacturers include it in their data sheets. So let's have a small recap of front-to-back ratio. The conventional thinking about front-to-back ratio is that if the front-to-back ratio is high, it means an antenna is good for dense collocation. So if the antennas are back-to-back and both have high front-to-back ratio, they will not interfere with each other. The reality is that high front-to-back ratio does not mean that antenna is good for dense collocation in every possible setting.
So I just find this to be a little bit disingenuous. He just said is good for dense collocation. Then he said wrong, not good for dense collocation in every setting. So he sets it up one way and then he switches it to something else, basically shifting the goalpost here. Is a good front to back ratio good in every setting? There's always going to be an asterisk there. It depends. But generally speaking, having a good front to back ratio is a good indicator of a high performance antenna. It is one of the best ways, particularly with point to point dish antennas. Having a high front to back ratio is going to tell you a lot about the side lobe performance, because the front to back ratio incorporates gain, which also tells you about antenna efficiency.
It's simply a misunderstanding. It's important to really get this right, because the next time you have a conversation about front to back ratio, you can be sure that if anyone is saying that high front to back ratio means an antenna is great for collocation, you know that the person is either misinformed, simply didn't go deep enough with the topic. High front-to-back ratio means that the back lobe is small. This is the lobe pointing in the opposite direction as the main lobe. It can also mean that the group of side lobes around the back lobe is small, depending on the definition or the way the front-to-back ratio was determined. The front-to-back ratio is very easy to understand. Looking at the radiation pattern of an antenna, in this example we show the pattern of a directional patch array. The front-to-back ratio is the difference between the gain of the main lobe and the gain of the back lobe, which is pointing backwards. In practice, front-to-back ratio is often determined based on the strongest side lobe, from a plus-minus 30-degree angle around the back lobe because of possible manufacturing, assembly, or material imperfections. Because of these imperfections, the back lobe might not just be a single lobe, but can be divided and fractured into several minor lobes around that direction. Nevertheless, back lobe is one of many side lobes antennas used in WISP industry typically have. So if back lobe is one out of many side lobes, then it's probably not so important. This is the typical error in
So it is important for comparison purposes. So if you're trying to compare two antennas, one has a good front to back ratio and one has a bad front to back ratio, you can tell about the quality of an antenna based on the front to back ratio. So while it doesn't give you a complete picture of every antenna in regards to side lobes, it gives you a good indication about an antenna's ability to focus energy in one direction relative to the amount of energy that leaks out the back.
Interpretation of front-to-back ratio. It doesn't say anything about all the other side lobes. When two antennas are exactly back-to-back, which, let's be honest, is quite a rare kind of scenario, high front-to-back ratio can help to decrease the interference level the radios see. But as I said before, typical antenna used with networks has a lot of side lobes, and the back lobe itself can be quite complex at the same time. As soon as there are more links on a tower or collocated antennas, are not exactly back to back, you are looking at noise issues coming your way because of all the other side lobes that these antennas have.
So again, the front to back ratio isn't going to give you a complete picture about an antenna, but it's going to give you a good idea about the antenna's ability to focus in a specific direction versus the amount of energy leaking out the back. And that ratio, you can then use that along with other things like gain, along with looking at the detailed antenna patterns to get an idea about the overall picture. You can use the ETSI mask, which they mentioned earlier in this presentation. They're going to be dismissing as well. But yeah, you need gain. You need to understand the front to back ratio. You need the ETSI mask. You need all of these things. You need the antenna pattern. That gives you an overall picture about the antenna. There's not one antenna parameter to rule them all. And if there was, it certainly wouldn't be this one.
High front to back ratio provides absolutely no protection in high noise environment.
So he just said front to back ratio provides you absolutely no protection in a high noise environment. And then on the slide here, it says high front to back ratio protects you only here. Which is it, no protection, or is it only protecting you in this way? In reality, if you have a good front to back ratio, then you're also likely to have a high quality antenna with lower side lobes as well. This is not an and or situation, but also these things are all related. So the ability of the antenna to focus in the forward direction is related to also the front to back ratio, and the front to back ratio is also related to side lobes. Although not necessarily, just generally speaking, yes. So generally speaking, an antenna with a high front to back ratio, a good front to back ratio, is also going to have suppressed side lobes.
So for urban and suburban areas with other wireless links in the neighborhood or even on the same tower, front to back ratio is irrelevant. These other links may be yours or competitors. Either way, they're using very similar hardware to yours, meaning their antennas most likely also have many side lobes that create noise, receive the noise, and anything in between through the rest of the side lobes.
So again, we're seeing noise coming from the side lobes. Magically, there's no noise in the main lobe. But noise comes in the side lobes, it comes in this back lobe, and it also comes in the main lobe. If you were to shape all of these into one giant main lobe, maybe you're going to have better noise resistance, maybe not. It just depends on the source of the noise.
Another parameter I want to mention is side lobe level. In practical life, its effect is similar to that of the front to back ratio. Let's have a look at the details of that. Side lobe level is the difference between the gain of the strongest side lobe and the main lobe. It is more useful than front to back ratio because it at least points out the strongest side lobe, which says a bit about antenna performance in high noise areas, but just a little bit really. If side lobe level is high, the strongest side lobe is close to having the gain of the main lobe, making it a very poor antenna for WISP networks. The issue with side lobe level is that it does not talk about all the side lobes an antenna has. Again,
so it does talk about all the rest of the side lobes that an antenna has because it's measuring the strongest side lobe. By measuring the strongest side lobe, you can know that all the rest of the side lobes are in fact not as strong as the strongest side lobe. Although it doesn't directly say anything about the other side lobes, it does say that they're going to be not as strong as the strongest side lobe. So you can get an idea about the performance of an antenna based on the side lobe level. And again, it's relative to, this is gain. Again, this is a gain measurement. It's the gain of the main lobe versus the gain of the strongest side lobe. Gain, again, is relative to a perfect isotropic radiator. So it is also built in measuring antenna efficiency as well. So that's why side lobe level is a very good antenna parameter for understanding the side lobe performance of an antenna, despite what RF element says here.
Ratio. It tells you what the strongest side lobe is at one frequency, but nothing about the rest of the side lobes throughout the useful bandwidth of an antenna.
That's not correct. So almost all antenna parameters are worst case numbers. They're the values of the worst case of the antenna across its designated frequency range. So in the case of side lobe level, it's the strongest side lobe relative to the weakest main lobe within the frequency range. So it's the worst case side lobe level is what you use for your data sheet. That lets the users of your antennas understand what to expect in worst case situations. They know that when they buy your antenna as per the data sheet, it's going to be better than what's described on the data sheet. RF Elements loves to confuse this. They love to confuse worst case antenna parameters versus average or versus typical versus best case antenna parameters. And a lot of times they'll take their typical antenna parameters, what they call typical, whatever that means, and then they'll compare that against their competitors' worst case values. They'll use that in a comparison table to show that their antennas are better than their competitors. They're just confused about this. So, as is the case of almost all antenna parameters, it's the worst case values that show up on the data sheets.
Which is the biggest issue with these metrics. In WISP networks, all side lobes of an antenna matter. To sum it up, not all antenna parameters are practically useful for WISP networks. It simply depends on the context an antenna is used in. In the end, it is up to the users and actually mainly the manufacturers to responsibly look at each antenna parameter and honestly evaluate whether it is useful in the framework of WISP networks or not. The conclusion for front-to-back ratio and side lobe level clearly says that these two are really not so important. They tell a very limited part of the story of the side lobes. And if you're wondering why WISP antenna manufacturers use them, show them in their data sheets and on, my guess would be it's simply a remnant of the times when these parameters were the only ones that were easy to determine and calculate without enough computational power.
So he says the reason why other WISP antenna vendors use the front-to-back ratio, side lobe level, is because we don't have enough computational power to determine beam efficiency. A lot of times I wonder about RF elements if they are incompetent or if they're malicious. It's really hard to tell the difference, but when I hear things like this, I really tend towards malicious. There's no way he could actually believe that. They just showed us what is involved in calculating the beam efficiency. It's simply a ratio of the energy in the main lobe versus the total energy radiated by the antenna. A ratio does not require a whole lot of computational power. When he says other antenna vendors must omit beam efficiency because they lack computational power, that makes me believe that they're grifters here. This is not them just not knowing what they're talking about. They know what they're talking about. They're purposely misrepresenting the truth.
You may also know about the ETSI masks, which to a degree also serve as a parameter that says how well antennas perform in terms of noise. Let's have a look at those. It is important to clarify that ETSI masks consider two main cuts of antenna radiation pattern, the azimuth and elevation. They consider two slices of the 3D radiation pattern, so again, rather completely incomplete, so to say, measure from the point of view of the whole 3D radiation pattern, all the side lobes that matter in WISP networks.
So he's saying that ETSI masks are incomplete because they only consider the azimuth cut and the elevation cut. And I guess he's saying that you should consider the entire 3D radiation pattern. This is a little strange to me because he's arguing that having two-dimensional cuts is not complete and that you need to account for the 3D pattern. But having two-dimensional cuts is understanding the radiation pattern in 3 dimensions. These two cuts are the most useful. So the azimuth cut lets you understand what that beam is going to look like on the azimuth plane, which is the horizon. It also lets you understand how to position your antennas with other antennas in the same ring of the tower, the same elevation on the tower, to position the antennas within the other antenna's nulls. The azimuth cut is very useful. Similarly, the elevation cut lets you understand what that beam is going to look like in front of the antenna, the beam propagation on the elevation plane. It also lets you understand how it's going to interact with co-located antennas above and below. So these two cuts are very useful. In RF Elements datasheets, they also just show you the azimuth cut and the elevation cut. This is the Ultra Dish 29. That's also true for the Ultra Horn. They just show the azimuth pattern and the elevation pattern. A 3D radiation pattern isn't necessarily useful. What you need is detailed information to use. And the basic problem with beam efficiency is it's just not useful. You can't do anything with it. It's not that it's incomplete, it's just not useful.
ETSI masks are observed at 3 frequency points, so an improvement, the beginning, the middle, and the end of the spectrum an antenna works in. Nevertheless, the rest of the spectrum, which is rather wide in the case of WISP networks, is...
He's saying that the ETSI mask only consider 3 frequency points, the beginning, the middle, and the end. RF Elements datasheets only show you 1 frequency point, 5.6. This is the Ultra Dish. This is supposed to be a wideband antenna operating from 4.9 to 7.1. They arbitrarily chose 5.6, that's the frequency point. But with antenna patterns, they're most likely to fall apart on the edges. That's where you're most likely to have problems with the radiation pattern, with side lobes manifesting. You want to see the edge cases. You don't want to see a cherry-picked value with a hand-drawn antenna pattern. You want to see a detailed antenna pattern, and it is helpful to see an antenna pattern at the beginning of the frequency range, at the end of the frequency range, and then it is helpful to have the ETSI mask to let you know how that antenna pattern looks relative to industry standards. This is cyber antennas, class 2 dish. The class 2 is conforming with ETSI standards, and we have 5.1 gigahertz, 5.6 gigahertz, 6.0 gigahertz, 6.8 gigahertz, and 7.125 gigahertz. So that's 5 different frequency points, and then we show the ETSI mask on each one of them. We have vertical and horizontal polarizations. So you get an incredible amount of detail, and this is the detail that WISPs need to understand how to use our antennas. This is not beam efficiency, a single number representing the amount of side lobes on an antenna is also not a useful antenna parameter.
Included in ETSI mask's definition. So again, not very robust measure. So how does one get to the ETSI masks and how do they look like? Starting with the polar plot, you may know from the antenna datasheets, we're drawing it on an XY axis or XY plot. ETSI masks are the blue dashed line, which says that the radiation pattern should stay below the mask so that an antenna can be declared compliant with a given ETSI norm.
If this is a 30 dBi antenna, then 30 dBi would be centered at 0 degrees. So it's normalized to 0 degrees. This black line represents the signal levels at any angle relative to the center of the beam. So at 90 degrees here, you can see that's at about negative 25 dBi. So negative 25 dBi from 30 dBi. So it's at about 5 dBi. And it's functioning like a 5 dBi antenna at 90 degrees. When you're perpendicular to the antenna, it's functioning like a 5 dBi antenna. And that's what this chart represents. The ETSI mask is this blue line here. You want your radiation pattern, that line, to be below the ETSI mask. The ETSI mask is a reference. It lets you know what a good antenna pattern looks like. And then if you see side lobes going above the ETSI mask, then you know that those side lobes aren't necessary. There are other antennas that will perform better, that will conform with the ETSI standards. And so the ETSI mask is useful as a frame of reference. It lets you know how this antenna performs relative to industry standards. That makes it useful. Also, getting the level of detail from this, they call it an XY plot or a rectangular plot, versus the polar plot. So this is showing the polar plot representation of the antenna pattern. This is showing the rectangular representation. It's the same data. It's just represented differently, but it's not exactly the same data because the polar plot, RF Elements polar plots, only go to negative 30 dB of detail. So you've got negative 30 here, you've got 0 here. It's only showing you the detail from negative 30 to 0. The rectangular plot here, this is negative 30, this is 0 right here. So it's only showing you the detail above negative 30. It doesn't show you all the level of detail below negative 30. On cyber antennas, antenna patterns, we've got 0, negative 10, negative 20, negative 30, negative 40, negative 50, negative 60, negative 70, negative 80. So we show a whole lot more detail in these charts. RF Elements generally only shows above negative 30, so it's just right here. This level of detail gives you obviously a lot more information, but notice you can't even conform to ETSI standards unless you are showing detail down to negative, it looks like negative 48 or so right here. This is obviously way more useful than this, way more useful than some arbitrary percentage of beam efficiency.
If the radiation pattern does not stay below the mask, the antenna is not compliant, which is the case for this example. The masks are easy to understand, and to their credit, They do consider the whole 360-degree circle of a radiation pattern, but unfortunately only 2 cuts of the whole 3D radiation pattern at 3 frequency points of the whole spectrum antenna may work in. So vast majority of the spectrum and radiation pattern is simply not included. Which is why in terms of interference suppression with networks, even these ETSI masks are really not that much of a useful parameter. So whenever you see an antenna being compliant with a particular ETSI norm, know that it does not really bring much added value in terms of noise suppression in WISP networks.
So it brings a lot of added value in terms of noise suppression in WISP networks because you can use it as a reference. So the ETSI mask is a reference value. It lets you know what you should expect from an antenna. Otherwise, it's pretty difficult to read an antenna pattern just on its own, know how that's going to compare to another vendor's antenna pattern that looks very similar, but there's small details, and it's hard to make comparisons if it's operating at different frequency points, has different grid lines and such. So the ETSI mask is very good as a reference, a frame of reference for understanding how this antenna pattern should look. And then you can see this is below ETSI class 2. There's other ETSI classes, of course. So you could have ETSI class 3, ETSI class 4, and then you would have higher levels of performance, higher standards.
At RF Elements, as a company, we are convinced about doing the right thing for the customer and the industry at the same time. So we investigated.
If they're concerned about doing the right thing for the customer and for the industry, the right thing for the customer and the industry is to provide as much detail as possible, as much education as possible on how to use that detail. What RF Elements is instead doing with their beam efficiency, they're making up an antenna parameter, calling it the most important antenna parameter, beating up their competitors, doing a very bad job explaining how this antenna parameter is useful for anything other than just saying that we have the best.
Textbooks ourselves found about beam efficiency, which is the most complete measure of side lobes out there if it's used well. When I say the most complete, I'm not just using empty overstatements or simplifications.
So with RF Elements, every day is opposite day. If he's saying he's not doing that, if he's not making empty statements and oversimplifications, then he's probably making simple statements and oversimplifications.
We're done with the following slides. I promise you will understand why. So beam efficiency is the answer to the question of side lobes. So despite you might have never heard about beam efficiency before, at RF Elements we do what we believe is the best for the customer, even if it means bringing something not considered or established before, and which might be different from what other manufacturers may be saying. Beam efficiency is a ratio of the energy.
So if they were interested in doing what was best for the customer, what they would do is improve their antenna parameters to be better than their competitors' antenna parameters. That's what they would do if they were interested in doing what's best for the customer. Instead, what they did is they went out and they found an antenna parameter that their antennas perform well with and declared that this is the best antenna parameter, the most important antenna parameter is what they declared. Then they beat up their competitors with this new ad hoc antenna parameter.
In the main lobe to the total energy an antenna radiates, making it a perfect and complete measure of side lobes. So how is beam efficiency obtained? Beam efficiency of an antenna can be determined through a measurement in an anechoic chamber like the one in the image. The antenna is attached to a rotary stage which rotates it in 2 axes, and it can measure the radiation pattern of an antenna, the full 3D radiation pattern.
So he's talking about beam efficiency measurement. So this is measuring the antenna parameter. The curious thing about this is if this is how they determine beam efficiency, why isn't that an RF Elements antenna? Why is that some random antenna that it looks like they picked off Google Images?
Based on the measurement, we can calculate the beam efficiency. Alternatively, if the model of an antenna is precise, or let's say an antenna is simple enough, we can use simulation software to do the same thing.
Okay, so which do you think they do? Do you think that they measure, or do you think they simulate? And I mean, the answer is obvious here, but this actually is an RF Elements looking antenna. They're clearly using this with their own antenna. Now, it's also interesting to note that not too long ago, he said that other antenna vendors must not have enough computational power. So apparently, they're using simulations, and they are using a desktop computer here to calculate beam efficiency. It's this desktop that is providing the computational power to calculate the beam efficiency.
The radiation pattern, and based on that, we can calculate beam efficiency. So, if beam efficiency is 40%, this amounts to the power that goes into the main lobe. So the remaining 60% must therefore be in the side lobes. No question there. And note that all the side lobes are highlighted. Yeah. So beam efficiency really includes all the side lobes of an antenna, not just one or a slice of the radiation pattern, but the whole package. Yeah, the full 3D data, which is what makes beam efficiency a complete measure of side lobes. Everything is included. And you can calculate beam efficiency for any antenna out there. Here you see the radiation pattern of a typical sector antenna. If beam efficiency is 58%, the rest of the energy, meaning the 42%, must be in the side lobes. This clearly tells you why the patch array sector antennas are really not so good for unlicensed WISP networks for the most part. 42% of the signal they radiate and receive is noise. Now, WISPs use quite a wide chunk of the spectrum, but in antenna textbooks, beam efficiency is defined at a single frequency and for a single polarization. Now, this is the case for most textbook parameters, actually, and it makes...
So most textbook parameters are not a single frequency and a single polarization. Antenna parameters are worst case values. So you've got your frequency range, and then you measure the antenna parameter across that frequency range, and it's the worst value within that antenna's frequency range that is used on antenna data sheets. And that lets operators know that if they use this antenna, they can expect at least this performance at any frequency that they may pick. And it's interesting here, you see beam efficiency up here at looks like 75%, and then it goes down to 25% or 30% here. They just arbitrarily picked a frequency point in the middle. That's the same effect as actually averaging. So if you average this, then you're also going to get a value somewhere near the middle. But what you need to know is worst case value, because you may operate at 6.0 gigahertz. And if that's within the frequency range of this antenna, and so you need to know how is it going to perform at any frequency range that I may pick. You may start up here, right? Or you may start here, and then you encounter noise and interference, and then you end up over here. But you need to have the edge cases. But for antenna parameters are worst case values. That's what they are. And RF Elements is confused about this. I think purposely confused about this, because what they like to do is they like to take their arbitrary value, their typical value, is what they call it. So in the case of VSWR, they'll take their VSWR typical, whatever that means, and then they'll compare it against their competitors' worst case value. And then they'll say our VSWR is better than their VSWR because they're measuring their typical value against their competitor's worst case value. Do they do that with beam efficiency? Probably. I mean, if they do that with VSWR, why wouldn't they do that with beam efficiency?
Sense to always consider any antenna parameter in the whole useful bandwidth antenna works and not just the single frequency point. And since WISPs use their antennas in a wide frequency band, it only makes perfect sense that an antenna should perform well in the whole bandwidth in all important aspects, including beam efficiency. Which is why we decided to actually average beam efficiency over the whole useful bandwidth, and on top of that for both polarizations. And the effect of this averaging is that it turns this textbook beam efficiency definition in a much more robust and reliable measure of the side lobe.
Okay, so they're taking the average of the vertical, and then they're taking the average of the horizontal, and then they're combining them into an average vertical and horizontal across the frequency range, and they're calling that their beam efficiency. The problem with that is if beam efficiency looks like the previous graph, or if the beam efficiency goes up and down and up and down and up and down like this, then the average is not giving you a complete information. It's giving you incomplete information. And you need to know how it's going to perform in the worst case situation, where, because you could use the antenna vertical polarity at 5.4, but this is assuming that all of the values are pretty close to each other. Then average seems reasonable. But if the values fluctuate a lot, and they could, then and by the way, averaging not useful, because that lets antenna vendors have a really bad value within the frequency range. So say for example, it looked like this, and then beam efficiency went down to a very low value at 5.1 and 5.0, shooting out radiation out the back, right? It's all side lobe and back lobe at that point. Well, if you're taking an average value, you could still pretend that your antenna is a good antenna. And RF Elements is known for this too. So with their gain drops off after 5.2. It just goes, and if you were to take average gain, then maybe their antenna would still seem reasonable. But that's why you need to have detailed data so that you can understand how it's actually going to perform. You need that level of detail. But also, you don't want to take averages for that reason as well.
Than the single frequency and single polarization definition, or anything else out there, really. Vast majority of antennas used for sector.
Okay, I'm gonna mute and hit play so you can see the asterisks here. Based on full wave EM electromagnetic simulation. So they're comparing, says beam efficiency examples, sector antennas, asterisks. Asterisks is, this is computer modeled. This isn't measured. So that goes back to measuring it versus modeling it. And this is modeled. It's theoretical. What they also said previously is that if the antenna is simple, then you can estimate it with a simple antenna. Or if you have detailed models, then you can model it accurately. Now, they are measuring their antennas for which they have the antenna designs. They have the detailed models. Yes, for their antennas. For their competitors, how do they get Ubiquity's 90-degree horn and Ubiquity's horn 530. How do they know what the beam efficiency of this is? Well, they modeled it in their own software, but they don't have the original model, presumably. So they are estimating, they're taking an estimation of their competitors' antennas and measuring the theoretical beam efficiency of their competitors' antennas versus the theoretical beam efficiency of their own antennas and declaring theirs better. That's what's happening here.
The RF elements horns, both symmetrical and asymmetrical, have beam efficiency between 90 and 95%. Now you can see other horns in this comparison as well. And this is to help you understand that it takes a considerable effort to design a horn antenna such that its beam efficiency is high. The stable and zero side lobe performance is not a given as soon as you have a horn, so be careful with that. But we do put a lot of effort into design of our antennas.
So they're saying that depending on the design, and then depending on the manufacturing of the antenna, you're going to have variation in beam efficiency. And so just because it's a horn doesn't mean that it's going to have high beam efficiency. But they're beating up their competitors for having low beam efficiency. How do they know how their competitors actually perform in terms of beam efficiency? They don't. They're taking simplified views. And again, RF Elements is known for comparing their best case numbers versus their competitors' worst case numbers. How do we know they're not doing the same here? We don't, because they're not showing us the work. They're not showing us the calculation. They're not even telling us whether they have the original model or how they created the models to do their simulation. They're showing us no work.
Likewise with the point-to-point antennas.
So they just beat up on Ubiquity and now they're beating up on MikroTik. Again, unfairly. So this is not a fair comparison. They're not showing us the work. They've got this subjective beam efficiency. You don't know where the main lobe ends and the side lobe begins. They haven't defined the first null. These are electromagnetic simulations. These are not measured values.
Arrays are again at the bottom of the beam efficiency performance due to the many frequency-dependent side lobes collecting and transmitting the noise, hurting any and every WISP network out there. Dishes are somewhat better. Generally, the bigger the dish, the better the beam efficiency becomes, if the antenna is carefully designed and well manufactured on top of that.
Carefully designed and well manufactured. So how do they know if these are carefully designed and well manufactured? Because they don't have the designs to create the beam efficiency values. These aren't even manufactured antennas. These are simulated antennas. So this is totally disingenuous.
Now with any antenna though, the compromises accepted at the design stage unfortunately cannot be compensated by manufacturing quality, since the real-world results are at best approaching the results which we get from the simulation. What is interesting here though is the ultra horn. Its beam efficiency is 99%. Now let that sink in for a second. Over the whole bandwidth of operation in both polarizations, the beam efficiency of ultra horn is practically perfect.
Call me unimpressed, because to me it seems like they went out and looked for some antenna parameter that they could use to toot their own horn. This is a cherry-picked antenna parameter. And then they cherry-picked how they calculate this. Of course, they're also going to cherry-pick what they consider the main lobe and the side lobes, because they haven't defined that. So this is just totally cherry-picked information here. This is not impressive.
Percent of the RF signal goes into side lobe. So if you ever wondered if ultra horn was worth the extra cash compared to a dish with similar gain, you have a very clear answer here. with 99% beam efficiency, is the best performing antenna on the market in terms of noise suppression.
So, a couple things there. In terms of gain, the Ultra horn has 24 dBi of gain. The Ubiquity Light Beam and a $69 integrated antenna has 23 dBi of gain. These are comparable antennas. Now, it's possible that the Ultra horn is going to outperform a light beam. The Ultra horn is what? 10 times the cost? So, is it worth the cost? It depends on the application. The light beam is obviously much better for most subscriber applications than the Ultra horn. So the Ultra horn is obviously not worth the extra money in terms of that application. You're not going to stick Ultra horns on subscriber roof. But also, the cost determines the application. You're not going to compare similar gain antennas when you've got a 10x price differential. What you want to actually compare is similarly priced antennas. So what's a similarly priced antenna to this? Cyber antennas, this antenna is half the cost of the Ultra horn. And this is going to outperform the Ultra horn every time, in every setting. There's no way that the Ultra horn would beat this antenna anywhere. But particularly in point-to-point applications, the Ultra horn has a 10 or 15 degree beam width main lobe. That's looking like a main lobe that looks like this. It doesn't matter if that energy is contained in the main lobe or in the side lobes. What you want is the energy focused at a specific point in point-to-point application. You want as much of that energy focused at a single point. Noise resistance is not having all the energy in the main lobe and no energy in the side lobes. Noise resistance is having as much energy at the specific point and as least energy everywhere else. By moving some of the side lobes into the main lobe, that may help if the noise is co-located. But if the noise is coming from between the two links, then having that wider beam width is not going to help at all. In fact, you could be picking up more noise from between the 2 points. Keep that in mind too. So the comparison is not similar gain antennas. The comparison really is similar priced antennas. And for the price of an Ultra horn, you can get a lot of high quality dish antennas, including deep dish antennas with excellent side lobe performance, as determined by industry standard antenna parameters, not nonsense antenna parameters like this.
Good thing is you can use Ultra horn not only for point-to-point, but also for multi-point coverage. With the option of tilting the antenna down, you can actually dynamically adjust the coverage. So it's really a very versatile tool, the best tool in terms of noise suppression.
Not the best tool in terms of noise suppression, but on using the Ultra horn for point-to-point versus point-to-multipoint, you can also do that with a 23 dBi dish. You can also use a 23 dBi dish for point-to-multipoint with good effect, particularly a deep dish. So if you have a deep dish that's 23 dBi gain or 24 dBi gain, that's about a 1 foot dish or a 0.3 meter dish. Then you can also use it for point-to-multipoint application. You just need to keep the stations within the beam width.
Beam efficiency tells you everything about side lobe performance. The higher the beam efficiency is, the better an antenna performs, period. So forget about front to back ratio, side lobe level, or ETSI masks, and really focus on...
Why would you forget about those other antenna parameters? Even if you fully swallowed everything that RF Elements is putting out there, why would you dismiss everything else? Why would you forget about everything else? Are they trying to educate here? Or are they just trying to market their products as the best? Obviously, they're just trying to market their products as the best. So RF Elements does not deserve credit for enlightening WISPs, for educating WISPs, for helping WISPs better understand how to deal with noise. They don't deserve that credit. They stumbled on horn antennas. Horn antennas perform well in noisy environments because of their narrow beam widths. RF Elements never understood that, so they went looking for reasons why their antennas performed well in noise. They came up with side lobes, but mostly what helps with co-located noise is GPS sync. And then they created this antenna parameter, this beam efficiency antenna parameter, as a way of explaining it, but they never understood any of it.
Beam efficiency of an antenna when dealing with noise. Not only it's the most complete measure of side lobes, but it's also extremely robust measure of side lobes because
neither complete nor robust. So complete would be taking into account the entire frequency range that the antenna is operating in. It would be giving you the worst case value, not averaging everything together. And to be robust, it really needs to be useful, right? So you have to have a way to apply this knowledge. It doesn't do anything for you. The only thing it possibly could help you with is product comparison. But you have to take RF Elements' word for it. And they're not a trustworthy source on this. They've proven that many times over.
See as well, ask them if it's averaged over the whole useful bandwidth and both polarizations to make sure.
RF Elements, how about you show us your work? How about you show us how you calculated these beam efficiency values? How about you show us the details, not just make blanket statements? How about you show us measuring the beam efficiency of your antennas and then comparing that with your modeled values? That's science. So how about you do some of the work rather than put it on us to ask our antenna vendors to conform to your nonsense antenna parameter?
The comparison is fair. Since it rarely happens that a wireless link is situated in a completely isolated place, the interference is present practically everywhere. Noisier the environment, the more important beam efficiency of an antenna you use becomes, because the higher the beam efficiency, the better noise isolation. And recently you can also hear claims from other antenna manufacturers saying, for example, this sector patch array antenna works like horn in terms of avoiding the noise. Similar statements. And to these claims, I would just ask a single question. What is the average beam efficiency of that antenna? Now, if the beam efficiency of that antenna is of similar values, then I would stay quiet and say, yes, I agree. But otherwise, if the beam efficiency is anything below 90%, you can be sure that they're really not the same, and the claims of the manufacturers are probably more of a marketing fluff than anything else.
So apparently, some antenna manufacturer, I have a guess, but some antenna manufacturer was saying their antennas perform like horn antennas. Probably what was happening there is an antenna manufacturer was making sector antennas that have narrow beam widths. With those narrow beam widths, you can have a sector antenna that performs similar to a horn antenna so far as a horn antenna has a narrow beam width. Obviously, RF Elements doesn't want customers to understand it's the narrow beam width of horn antennas that make them perform well in noise, not the no side lobes. And so it appears that they created this beam efficiency as a way of debunking their competitors' claim their sectors were performing similar to horn antennas. That seems to be actually what's going on here.
And in the following section, I will tell you about the practical implications and consequences. So using an antenna with high beam efficiency, we can sum up the effect of high beam efficiency antennas into one statement: higher throughput. In a sector with no other links in the area, you don't mind the side lobes, but as the number of sectors grows, their side lobes cause the noise floor to rise. And higher noise floor equals lower SNR the radios are working with, and eventually lower throughput.
So what causes the noise to rise is these wide beam widths. So you can see they're actually contradicting themselves right here, because you've got this sector. This is all part of the main beam. This is not side lobe. This is part of the main lobe. And they're calling that noise. You could have 100% beam efficiency, and you can have a main lobe shaped like this that's picking up all of this noise.
The beam efficiency of patch array sectors is on the order of 60%, as we saw. The remaining 40% of the energy is in the side lobes that collect and transmit interference to other links within yours, but also competitors' networks, obviously. So low beam efficiency equals lower throughput, consequentially more unsatisfied customers, constant issues with your network, and that keeps you unnecessarily busy. Low beam efficiency of dish antennas works in a very similar way. It's really the same, but not different, really. The side lobes collect the noise from its surroundings.
So just notice there's a single point here, and you need to have your signal focused on that single point. Everything not pointed at that single point is unnecessarily wasted energy. It is picking up noise from unintended directions. It doesn't matter if the beam efficiency is 100% or if it's 1%. What you care about is how much signal is focused at that single point and how much of the beam is picking up noise from unintended directions. The more unintended directions, the more noise that you're going to pick up. It's not the beam efficiency, though. It doesn't matter if it's main lobe or side lobe or whatever. Here is noise. This is wasted signal. This is wasted energy. This is poor performance. The noise doesn't stop magically where the side lobes supposedly end. So again, remember I was saying, where does the main lobe end and the side lobes begin? As far as picking up noise, you're picking up noise from all of this. And it's only right here that you actually care about. So any signal that isn't being sent specifically to the other point, that is wasted signal and wasted energy. Now, if you have a 90-degree symmetrical horn, it has 100% beam efficiency. You're still, for point-to-point application, that's a terrible antenna, unless you're in very close proximity. But the same is true here. So when it comes to understanding how an antenna is going to perform in noise, beam efficiency isn't doing it.
And transmitted to all neighboring links. Again, whether it's a backhaul link or a distant narrow sector, the beam efficiency around 40% means low throughput in high noise areas. And on top of that, susceptibility of these links to anything that's happening in the surroundings. If someone puts up a new link, you instantly see the result on your network performance. Now, replacing the low beam efficiency patch array sector by horn antennas with beam efficiency up to 99%, the noise level in the urban and high density areas is effectively avoided. Because high beam efficiency means no side lobes. No side lobes means no interference. The final effect is...
So no side lobes means no interference, is what he just said. Now imagine this is your sector, right? And your subscribers are located here. And you've got home Wi-Fi routers located all throughout the sector. And you've got competing CPE antennas all throughout the sector. You've got neighboring towers in the sector. Obviously, no side lobes does not mean no interference.
high throughput and network stability. Addressing the most pressing problem of WISP.
So he's saying that the noise is here. The noise isn't there. The noise is everywhere.
This is much more straightforward. Now, only one advice here. Use antennas with high beam efficiency. High beam efficiency equals to high throughput. That equals eventually to happy customers and a joyful life as an internet service provider.
So notice here, their diagrams show narrow beam widths. So they show sector division, show narrow beam widths. Yet RF Element still doesn't understand. They still don't get it. They actually drew it out on a diagram here, but they still don't understand. So they got 3 sector antennas providing service to all of this area. They say the noise only comes from co-located towers. They don't understand that noise also comes from the sector. Even though they made a drawing here showing how this network would perform better than that network, but not because of the beam efficiency, because of the narrow beam widths.
Actually, it gives you the freedom and time to, you can switch from running around servicing the faulty and problematic links or talking to angry customers to actually start thinking about, well, how can I expand my business? How can I do even better? And that's really something that's invaluable. And the radio manufacturers are actually also trying to help with the noise naturally. The GPS synchronization, ensuring that the radios in your network transmit and receive at the same time, protects you from self-interference, but not from the side lobes of the competitors' antennas. Now, high beam efficiency ensures that you do not have to...
So GPS sync completely eliminates self-interference if you can GPS sync all of your co-located radios. But the noise and interference doesn't just come from the side lobes.
Worry about the interference at all. It does not receive it. So you don't need to try to deal with it in the first place.
So he's saying you don't need GPS sync, apparently, if you use their antennas. That's the claim. Now, anybody can have multiple radios co-located on a tower. They're set up as access points. But if you scan as a station from one of those access points, you can see how strongly that access point sees its co-located access points. Now, if you're running RF Elements antennas and have no side lobes, you don't need GPS sync, then they're not going to see each other. But obviously, they're going to see each other. Just keep that in mind, and that the signal level that they see each other at, that's the noise and interference that they're going to cause to each other. Yes, you need GPS sync. GPS sync gets you so much more.
So beam efficiency is a very practical antenna parameter. Now, before the discussion about the side lobes was limited to many versus little or yes versus no, beam efficiency provides a number from 0 to 100%, and it's super easy to compare side lobe performance of antenna.
A little too easy.
Now, the front to back ratio or side lobe level are parameters that are really not so important, not useful in WISP industry.
So notice RF Elements is calling side lobe level and front to back ratio myths, saying parameters are largely confusing, saying that antenna parameters only show one frequency point and one polarization. False. Saying unclear antenna comparison. Also false. In fact, the whole problem with beam efficiency is RF Elements is the only antenna vendor using it. So it's not useful for antenna comparison, although RF Elements might like it to be, although RF Elements claims they know the beam efficiency of other antenna vendors. It is not useful for comparison. Again, every day is opposite day with RF Elements.
Because they only consider one side lobe or one lobe out of many antenna might have. So beam efficiency, on the other hand, includes all the side lobes, which makes it very useful metric. Including all the side lobes removes any ambiguity. You can be...
So they're saying now, and they have a thumbs up, averaged over the band and polarizations, that makes it less useful, not more useful. It doesn't have a clear definition because they haven't defined the first null. They haven't defined where the main lobe ends and the side lobes begin. All side lobes included, okay. Easy comparison, no, you can't compare to other antenna vendors because no other antenna vendors use this because it hasn't been defined.
This metric is reliable. Always ask whether a parameter is a single frequency or wideband. In WISP industry, wideband is simply a must. Because the spectrum is shared by many, therefore wideband performance is vital. And RF element's addition to the beam efficiency definition is to average it over both polarizations and the whole antenna bandwidth.
So it's ironic that RF Element says that their antennas have wideband performance. Their 5 gigahertz antennas don't even cover the entire 5 gigahertz range. So they often confuse the frequency range of their antennas. So here it says 5 and 6 gigahertz unlicensed spectrum band, wideband performance, 2,225 megahertz wideband. The 5 and 6 gigahertz bands, they keep on saying this. Down here, they say 4.9 to 7.125 gigahertz, or 4,900 to 7,125 megahertz on the waveguide port. But they say check the spec check for performance data of the particular combination of feed, TPA, and antenna. There is no twist port adapter that allows this frequency range. There's no twist port adapter that I'm aware of that even covers the entire 5 gigahertz band. RF Elements has been making 5 gigahertz antennas for more than a decade. They don't even have antennas that cover the entire 5 gigahertz band. So ironic that they think that they have wideband antennas.
Not do better than that. It's really the most one can do in terms of how useful this parameter can be. So beam efficiency is the ultimate measure to judge antennas by in WISP industry. And it is a tool in your hands eventually to make better decisions for your business. So please use it, and ask for it if an antenna you're looking for doesn't have it in the datasheet. To make it easy for our customers, we added beam efficiency of our antennas into all our datasheets, and we are a transparent manufacturer and want to provide our customers the information that's important.
So he says he wants to provide the information that's important. Take, for example, excellent VSWR on the UltraDish 29 wideband. I'm going to search for VSWR. There's 2. VSWR, check our online spec check for performance data of the particular combination of feed. They don't even tell you what the VSWR is of their antennas. They say they want to give you the information that you need. I'm going to search for isolation. No return value. So they don't include VSWR. They don't include isolation. I'm going to search for gain. So it says nominal gain, whatever that means. So they don't include measured gain. They include nominal gain on their antennas, so on their data sheets. So gain, no. VSWR, no. Port isolation, no. Rectangular plots that show you detailed antenna patterns, no. Both vertical and horizontal polarizations on the antenna patterns, no. Multiple frequency points on the antenna patterns, no. ETSI mask, no. When they say they want to give you the information that you need, beam efficiency, that's being disingenuous. They're going to continue on promoting all their other beam efficiency videos. Is there anything left over? Leave it in the comments. Let me know if I missed anything about beam efficiency that still needs to be addressed. I think I've done a pretty good job. Thanks for watching.